Okay, so today's speaker is Surojit Ghosh, and he's from University of Haifa. So he will speak about higher differentials in Adam's spectral sequence. So it's a pleasure to have him. So you can start.
Thank you so much for inviting me here. Thank you. So today I'm going to talk about the higher differentials in Adam's spectral sequence, and we know that in algebraic topology our fundamental object is to computing the higher homotopy groups of at least for sphere. So Adam's spectral sequence give a it's one kind of base tool to compute this kind of homotopy groups of sphere, or rather some good spaces. So the point is, whenever we want to compute the Adam's spectral sequence, there is some problem to understand. We don't have a good tool, like we don't have a good machinery to calculate all the differentials. So whenever you want to compute any spectral sequence, you have to analyze the all pages, and you have to go to the infinite page, then you have to understand something. But what I'm going to say today, that you don't need to look into the full-fledged Adam's spectral sequence that to understand a certain finite stage of page. So you have to, so it's something connected to the constructive Postnikov sections of some mapping algebras, and how the differential is connected to the Postnikov sections. So this is the whole point of my talk, and how you can efficiently compute the higher differentials in Adam's spectral sequence. So okay, I'll begin with some basic of homotopy theory. If somebody don't know, that's why I just want to say something about the basic. So we start with the homotopy. We know in topology we study homotopy for the topological spaces, and for the continuous map up to some certain relation is called the homotopy. And a homotopy is actually a deformation of continuous map from one to another in a continuous way. So just this picture will give you the flavor for the homotopy. Like if you start with a homotopy between two maps, it is a continuous deformation from the cylinder top to from the top of the cylinder to the bottom of the cylinder in a continuous way. Anyway, so the fact is, whenever you have a homotopy, it gives an equivalence relation on the set of maps from X to Y, and the set of maps under this equivalence relation is called the homotopy class of maps. And a class, a map F, we denote by the bracket F for the class of maps, and for the homotopy class of map under the relation homotopy. Okay. So now the point is, we would like to understand what is the homotopy groups and how one could compute this. So a homotopy groups is something where you know about the first space. So your first space is something specific. It's a sphere. So whenever you have a sphere, it comes with a group structure. So you get something called a homotopy groups if you put X equal to sphere. So a homotopy groups is nothing but the homotopy class of maps from the sphere to Y, and the topology comes from the subspace topology of the RK plus 1, and it has a natural group structure. I will describe it in a minute, but we know for K equal to 1, it's a fundamental group with the multiplication given by the pinching. So you have a circle. So if you take two class F and G, it's a map from a circle to Y, and you can pinch the circle to make it two joining at a point, and you define F on the top and G on the bottom, and it gives this composition gives you an operation. It's called F plus G, and it turns out that under this operation, pi U1 X is a group. And if you go for the higher dimensional sphere, you will get a group structure. Actually, you will get an abelian group structure for the higher dimensional sphere. So the fact is, we would like to compute these homotopy groups, and we know from our basic algebraic topology knowledge that the homotopy groups of sphere, if your homotopy dimension is less than equal to the sphere dimension, we know all the computations, we know this is 0 if your homotopy dimension is strictly less than the sphere dimension, because we know in a sphere you always can contract a circle inside a sphere. So it's so the first equality is nothing but a generalizations of the seeing a circle inside a sphere, and the second one is due to the Hopf, and it's called the Hopf-Degree theorem. Our circles are something very special. We know everything about the circle, and all the higher homotopy groups are circles are zero. And the point is, it is not true if you want to compute for the higher sphere, at least for the sphere 2. So the computations of higher homotopy groups is still a very difficult and fundamental problem in algebraic topology. So what are the tools available? So what kind of tools we apply to compute the higher homotopy groups? First, we know something called 2 out of 3 property kind of things. Like if you know 2 and you can fit inside a long X sequence, and you can compute the other one using the long X sequence data. It's called the fibration, and a fibration it's some kind of generalizations of the fiber bundle that we know. Fiber bundle is a continuous map, which is looks like a product map on certain specific intervals which cover some specific open set which cover your base space B. So this is known that fiber bundle is some kind of generalizations of it's kind of twisted product map, okay, with some twist. So, and if you take a point in B, and the pullback is called under this map, B is called the fiber of this map, and this fiber is denoted by F. And as you know, we know the example of tangent bundle. So you know the tangent bundle is a right example for a fiber bundle, because if you take a point here and you pull it back using the tangent bundle projection map, you'll get the manifold itself. So it has the same fiber as the base. So this is a concrete example from the geometry, and fibration is some kind of homotopic version of this fiber bundle. So I don't want to go into the exact definition of the fibration. It's some kind of lifting up to homotopy. So yeah, so some property which so you understand clearly about the fiber bundle, and this is some kind of fiber bundle under some homotopy relation. So yeah, so but the fact is much more important than the definition. Like if you have a fibration with a fiber, if that is the P inverse of a point in here.
Sure.
Yes.
Yeah, I didn't know about it.
Hello, can you hear me?
Yes, I can.
So somebody is asking question. I can't hear the question.
Is there a question? Maybe not. Maybe it's just the background noise. I don't know.
Okay. Sorry. Okay. So whenever you have a fibration with a fiber F, we can talk about the long X sequence associated to the fibration. And what is the long X sequence? It's just the sequence of maps. If you take the kernel of the later one, it's equal to the image of the previous one. So it's every pair of maps in the consecutive way fits into like a kernel of the last one will equal to the image of the first one. So this sequence is a very useful tool to compute the some of the data from the homotopy groups. And for an example, we talk about the Hopf fibration. So if you start with a 3-dimensional sphere, and we can, you know, under the stereographic projection map, we can view this 3-dimensional sphere as a Euclidean space with an additional point infinity. And so what is the identification like this? If you start, so this infinity is the North Pole. So if you draw a line from the North Pole, and it will hit somewhere in the R3. So if you draw the all trajectory of this map, it gives you the disjoint union of the circles, but they are actually linked circle with an additional line, which is the line, you know, the line is the circle at the infinity. So you can view the R3 as a disjoint union of circle with an additional line, and all the circle are linked in a disjoint way. They're not touching each other. And now you can take a ball inside R3 and send everything to its boundary. So it will gives you the S2, the two-dimensional sphere. And then you can have a map H. This whole process of this thing gives you a map H from your three-dimensional sphere to a two-dimensional sphere. And by the description using the stereographic projection, we understand the fiber are nothing but the circles. So you have a fibration, rather it's a fiber bundle, and you can then automatically you have the long jet sequence in homotopy groups. Then you can use the homotopy groups information of what we know from our earlier knowledge, like these homotopy groups of circles are it's very easily computable. So these two are 0. These two ends are 0 if you take I equal to 3. And this one is the Hopf degree theorem. It still gives you Z. So this we get the pi 3 of S2 is Z. And this is the first non-trivial homotopy group for the when your homotopy direction is bigger than equal to the dimension of the sphere. So this computation is due to Hopf, and this computation gives you evidence that you have a lot of homotopy groups when you increase the homotopy direction rather than the space dimension. Okay, so the next tool one could think of is so this data is not sufficient for many of the spaces. You can't do this thing, this fibration technique to compute all the homotopy groups, but you can fit a lot of fibration together in a decent way. So we can talk about the tower of fibration. So a tower of fibration is a sequence of maps where all these verticals are the fibration map, and all the horizontal maps are the fibration map, and the verticals are the fiber, including inside the total space. So all this right angular thing is a fibration. So all these right angles are a fibration. And so once you have this tower of fibration, we know for each of these right angular these two maps, since it is a fibration, you have a long sequence in homotopy. So, but they are connecting in a good manner, and all this together gives you an interlocking sequence of homotopy sequence, homotopy groups. So this red one, like this red map, it's comes from this fibration, this right angular, and this blue maps comes from this fibration. Okay. And we can see this all together, they fit inside in a good way, such that what we want to do, we want to compute now the homotopy groups of something in this tower of fibration. So we have a tower of fibration. Then if it is a finite tower of fibration, we can talk about the limit of, actually we can talk about the limit for the, like the homotopy limit of the tower of fibration, because they are the fibration, they are the actual limit. So we want to compute the homotopy groups of the limit of this tower of fibration, and using the data from the fibers. So that is the whole point of the spectral sequence business. So what is spectral sequence? Spectral sequence is something where we would like to compute the homotopy groups of a space, where that space can be written as a smaller, it's a filtered way, in such a way like this YS, and they have a fibers where the fibers are very well behaved in terms of the homotopy groups. So this is the whole idea to for the spectral sequence. So we want to analyze the elements of this pi n of y in terms of the elements of pi n of fs, the fibers. So let's look at the picture again. So we would like to compute, understand the elements of these homotopy groups. So let's take some element here, and since it is a limit, so it will gives you at some finite stage. Let's like, okay, this gamma is the finite stage limit. So gamma, we take gamma here, and the one representative of the gamma should be inside ys plus 1 at some large s. And you can send this gamma to a beta, and if you compose with this delta s, this composition is a part of the long jet sequence, so this is 0. Okay, now if alpha is an element such that this whole composition, like if delta S composition, that is blue, this red is going to 0, if you get a map element like alpha here, then you can define and map from alpha to this image of this boundary of our pre-assigned element gamma. Okay, so what is the point of all this discussion? Like if your map delta A is composed J is this red and blue composition is 0, then it forces to give you a map from this fiber at some index to a fiber here. So here the index of the homotopy direction is decreasing here, and the fiber direction is increasing. So this gives you a map in the second page of the spectral sequence. So all together I can summarize in such a way that you have a successive approximations of your target space Y in such a way that you only involve the information of the fiber, and once the first this blue and red map composition is 0, then you will go to the second stage, and once the second map, this D2 is 0, then you will go to third page, and so on. You will have an infinite number of pages, and all these infinite number of pages will group together to give you the answer for your homotopy groups Y. Okay, but if you look these maps carefully, we are actually basically cheating somewhere, because you know, we're supposed to use the information for the fibers, but here to understand the map D2, we are going through the all this YS plus 1 YS and this thing. So we are using somewhere the information about the fibration map also. But the spectral sequence is such a beautiful thing. They don't remember anything about this process that I described. It will only remember this dashed arrow. So altogether it will give you some, you know, it's to describing these things. It seems that we are using this data, but at the end it will not use this data anyway. So anyway, so we have this gadget. So we will try to understand how you can understand this D2 or D3 or D any higher differential in a better way. Okay, so now the point is how we, so what is the objective to compute? So as I claimed that whenever you would like to compute the homotopy group of space Y, we would like to fit this homotopy this space in a tower of fibration, so that the fibers are very easy to compute in terms of the homotopy groups. And we all know the Eilenberg-Maclaurin space, which I'm going to describe. So that I'll describe some space that have a very easy computable homotopy groups. So what is that? It's called the Eilenberg-Maclaurin space. And whenever you start with an abelian group A and an integer which is non-negative, then you have a topological space associated to these two data, the abelian group and N, and which is uniquely determined up to this equation. The homotopy groups is concentrated in exactly degree 1 and degree N. Okay. So, but the fact is, these objects will you know, represent the cohomology groups, and this information is much more involved, because if it you know, it's represent the cohomology group, then automatically it has an action from the, you know, if you have a homotopy class of maps between Eilenberg-Maclaurin space, it will act on this data using precomposition. So it gives an operation on the homotopy cohomology functor, and these operations are the cohomology operation, and this plays a crucial role to compute the homotopy groups of topological spaces using the spectral sequence gadget. Okay, so now our first attempt to understand the Posnikov sections is why we want to understand Posnikov sections. Posnikov sections is a tower of fibration which we are looking for, which has a very good control over its fiber. All its fiber are very computable homotopy groups. They are Eilenberg-Maclaurin spaces, And so let me define what is the meaning of a Postnikov section for a topological space. So given a topological space X, and for each n non-negative, we can assign another topological space P and X, which is described by this homotopy information. So that the homotopy groups, if you compute the homotopy groups, it vanishes if you go beyond n, and it will be exactly the same up to n dimension. So what does it mean? It means we are killing the homotopy groups of X after dimension n. So if you look at the simplicially, so simplicial as a simplicial complex, P and X exactly equal to all the simplex, all the simplicial homotopy information are same for up to dimension n, up to simplicial dimension n, and then you have a more higher cells in the higher dimensions. But the fact is, for this Postnikov section construction, you have a tower of fibration where the homotopy fibers or the fibers are nothing but our Eilenberg-Maclaurin spaces. And but it is this, if you take the limit, or rather homotopy limit of this tower of fibration, you will get a copy of X, and this should be a right candidate to compute the homotopy groups using the spectral sequence. But the spectral sequence gives nothing to you, because if you consider, let's get back to the spectral sequence page. So if we understand these fibers are Eilenberg-Maclaurin spaces, so now, and so that means this guy is non-zero if this homotopy index and the fiber index are same. Otherwise they are zero, because this guy is an Eilenberg-Maclaurin space. So once it is non-zero, it forces this guy is zero, also this guy is zero, and so on. So that means in the spectral sequence, your this composition is zero, because this is your it hits either to zero, or or a source is zero, and also your D2 is zero, and so on. So all the differentials in this Adams spectral sequence, in this spectral sequence associated to the Postnikov section tower is zero. Therefore, we understand that this spectral sequence gives nothing. So this is not a right description for a, this is not our right tower of fibration. So we should think of that what is the next choice, so that we can have a more information here. Also, we can compute these fibers very easily. So first choice we should think of, like, we can think these fibers as a product of Eilenberg space. We know the computing the product under homotopy is very easy, because it will give you the it respect the product, and also you know how to compute the homotopy groups of Eilenberg space. So the next thing we try to compute, we try to consider a tower of fibration, so that the fibers are product of Eilenberg-Maclaurin space, and we know this kind of situation is called the Adams spectral sequence. And Adams spectral sequence, we know it is a very useful tool in homotopy theory to compute the homotopy groups of Y, and how this sequence constructed. It should require a it's a tower of fibration, and we associate a tower of fibration to each space. Using the cohomology information, and where this Ks, the general fiber, is nothing but the product of Eilenberg-Maclaurin space, and 2 is, if you want to compute the E2 page of this spectral sequence, this involves the information about the cohomology of our space, our target space Y, and a action of the homotopy class of maps between Eilenberg-Maclaurin spaces. So this whole thing gives you the information about E2 page of this Adams spectral sequence, because we already have seen that the Adams spectral sequence is nothing but a derived functor over which can be computed over the standard algebra structure. Like it is an Xed over standard algebra, and this guy encodes some of the information about the standard algebra. So this whole E2 page is nothing but the cohomology with this additional action. So now point is, can we make these things more precise? Can we define some gadget such that they will encode all this data? So the right choice to understand these things is the mapping space construction. So let me recall a little bit about mapping space. So we know for any topological space X and Y, we can talk about the set of maps from X to Y, and we know it has an inherited topology coming from the compact open topology. And crucial point, we should and under this topology, the composition is continuous. So we should. So this part is crucial to analyze this kind of object. So what we got, we start with topological space, and we get another topological space with some other topology. With if you compute the zeroth homotopy groups of this, I mean the path component of this object, that will gives you the homotopy class of maps X and Y. So this small information gives you a lot of things in the Adams spectral sequence. Like first of all, this is an aside. Like this is so all the topological space behaves like an enriched category over themselves, and they form an infinite category. And this is an aside. So it's in modern day we are using the infinite category data, but it's okay to have work inside the enriched category like this. So anyway, this is not our point for today. Like the fact is, the zero Postnikov section, we know if you try to compute the zero Postnikov section of the mapping space like this, it will kill all the, as you have seen, that it will kill all the homotopy groups after the zero dimension. So that means it will gives you only the path component data of this topological space. So this is nothing but the homotopy class of maps. Second, if you want to understand what is the first Postnikov section of this mapping object, that is nothing but the homotopy classes of homotopies, and sometimes we call it tracks. So this P1 encode the information about tracks. So this is in one word, we call it tracks. So so the idea is we want to understand PK, the PK Postnikov section of this mapping object, and we understand that this capture a lot, not the whole, but a lot of information about the higher structure in the Adams spectral, or actually higher differential in the Adams spectral sequence. So let's make this mapping algebra. So you know, in Adams spectral sequence, we are trying to build the Adams spectral sequence whenever you have a tower of fibration with certain fibers. So we would like to understand how it behaves when you consider all the mapping spaces. Like if you take the functor like X dash, and we analyze this kind of object, how it gives the all data of differential. So let me say a motivation for this things. So we just want to take a simple tower of fibration, like you have one fibration, and if you have a space Y such that this composition, this vertical then horizontal composition, this F and G is 0, then we know that this 0 means if it is null homotopic, then it's factored to the cone. So null homotopy gives you a maps from here to the total space E, and since this composition, this zigzag kind of composition is 0, it will induce a map on the suspension. So what we understand from this whole picture, like once you have, so this composition is 0 is kind of the first D1, the differential. This plays D1 for a single fibration. So if the first differential is 0, you will get some map from the suspension to the base. So, and also you have to record the information of E also, because the H bar comes from H. So you have to record the information about E and B. and where your space x, y is fixed here. Okay, so that means whenever we would like to understand the fibration that gives you, if this composition is 0, that gives you a map uh, from the suspension of y to b, and it comes from this kind of map H, this null homotopies. So and one point is that if your y equal to sk, so this null homotopy, that induced map from the null homotopy gives you the information about the differential, the boundary in the long X sequence, which is the connecting homomorphism for the fibration. But this is not the point. The point is, if your fibration is fit inside the tower of fibration, then this D2 differential. So let me give you another again. So what is this composition? This composition behaves like a D1 in our spectral sequence. And once you have the D1, then you get a map where this information coming from the homotopy information. So the point is, if you want to understand the D2, so we already described, you can define D2 once your D1 is 0. So you consider D1 is 0. So if you now you want to understand D2, so D2 information is coming for this homotopy, coming from this homotopy information, right? And so this is somehow behaves like D2, but it should be go inside the fiber. But anyway, so it will gives you, so the D2 depends on this homotopy and these two maps, okay? So if you want to compute the D2 differential for a tower of fibration where this small fibration fit inside the tower of fibration, then the second differential of the random spectral sequence can be determined from this homotopy information. And we know the homotopy of homotopies sit inside the first Postnikov sections of a section of the mapping space that I described a few minutes back. So we understand that the D2 differential in the spectral sequence depends only on the Postnikov section, first Postnikov section of these mapping spaces, where this dash space is varying, like it could be E, it could be B, it could be anything, okay? So that just to see, because it could be H or H bar, anything. So all two information should fit inside this thing. So what we understand, like the D2 info, to compute D2 information, you need the P1 information of the mapping space, and for the all varying space here. And we can generalize this concept. So similarly, for the higher differential depend on the higher Postnikov truncation. And you understand, if you know the all D2 information, then you can take the kernel and image, and then you can define that your E3 page. So we understand that to define, to understand a certain finite number, like for example, if you want to understand the E3 page, it is nothing but the whole information is encoded in P1 Postnikov section. We already have seen that for the E2 page of random spectral sequence, we have seen that this is encoded in the P0 of the only the P0 information here, right? Like I can give you another motivation for this. Like all this gadget like this home Y2 anything is called something like a mapping algebra, but we would like to fix this space. Like we don't want to say like all spaces, but we have some specific objects. Like for Adam spectral sequence, we know these all the fibers are nothing but Eilenberg-McLean space. So we would like to say something about we need some mapping algebra, mapping spaces where the source is Y and the target is Eilenberg-McLean space, product of Eilenberg-McLean space. But we know the Hom is respect the product, and the simplicial Postnikov section also respect the product. So it is enough to understand the mapping spaces from Y to Eilenberg-McLean spaces. So you don't need the product. So yeah. So the upshot is, like, you can define a mapping algebra using all this motivation that I gave. So mapping algebra for space Y is a collection of spaces where for each an abelian group and an integer n or non-negative integer n, you define the mapping space from Y to the Allen-Bergman spaces, and with a continuous action of this object, like all maps from all continuous maps from Allen-Bergman spaces. But the point is, if you take the zeroth homotopy groups, the pi zero of this collection, then what you get? You get the homotopy class of maps from Y to K pi K A N, and this is nothing but the cohomology of Y with coefficient in A, and this gives you the information about the homotopy class of maps from these two Allen-Bergman space. So that means this mapping algebra, this definition encodes the definition, this definition encodes the all information about the E2 page. So pi zero of this mapping algebra encodes all the differential, all the information about the E2 page of our Adams spectral sequence. So this gives you the motivation for to say something about in general. So in general, we can define for any collection of these spaces, like any mapping algebra, we can define a Postnikov section as an individual mapping Postnikov section of the mapping spaces. And with this notation in hand, we can state our result. It says, if you want to analyze the Adams spectral sequence and you are in some pages, like some finite number of pages, you want to describe what is the information you need to describe the ER page or ER plus one page, then you don't need the whole information about the mapping algebra. Like, so what you do, you don't need the all maps from Y to all product of Allen-Bergman space. You don't need that. Usually we use these things, but we only need some truncation, some Postnikov section of our mapping algebra for Y. So if you want to analyze for the Adams spectral sequence for Y, so we just described for Y, we have this mapping algebra, and we can have a truncation using this definition. So the dr differential is actually not, it not depends, all the information to compute the dr differential is encoded inside this truncation. And okay, and this gives you a lot of comfort to compute the, it's not it's not that computable. There is, you can say that how you can compute exactly what is the form of the differential, but it's I don't know yet, but it gives you some guarantee that you don't need to look into the later pages to understand. For some finite number of pages, you don't need to go for the all information. Some less number of information is okay for to understand the ER plus one page for certain R. So what is the idea for the proof? So as we have seen that the dr differential, the R differential of any Adams spectral sequence is encoded here, like so we can see from here, like just a second. Yeah, so we understand that any information is encoded here, right? So we want to analyze some element here, and it gives you certain maps between here to here. So but how you construct this map, this construction, remember this, the spectral sequence don't remember these things, but if you try to do that by hand, it involves this filtration of your space Y. So it somehow says that the differential D2 differential is involved all the maps, yeah, all the maps in the different stage of your fibration, tower of fibration sequence, and this guy YT, this should be the fiber direction. This is the tower of fibration direction, and this is the fiber. Sorry for the typo. And for the Adams spectral sequence, we know this direction is nothing but the product of Allen-Bergman space. and since it's commute with the product, and the simplicial Postnikov section also commute with product, so it just gives you the information about the mapping algebra for Y. So for the Adam spectral sequence, you can see this is nothing but your Postnikov section for your mapping algebra for Y. So the proof is a bit involved, but it's some kind of flavor of this proof that, yeah, you can understand your differential using this some small data of your whole thing. So the thing is, we have done these things for the spectral enriched category, like all the symmetric spectra also. This whole program goes well in the spectrum category also. But yeah, but we are looking for a more computable thing. It's not that much computable, but it's yeah. Anyway, thank you. This is this is the end of the talk. So you can ask me question if you want.
Okay, thank you very much, Surojit. Are there any questions from the audience? There is a question. I think I see your hand, Matthew.
Oh no, sorry, that was my trying to give the applaud.
Oh, I see. Sorry, that was not the raising hand. Okay.
That was the thank you indication.
Okay.
Can I ask a question?
Yes.
About your well, I saw your recent archive posting with David Blanc.
Yes.
And that's about spectra. Can I just ask a technical question about it?
Yeah.
I may have missed this. I've read it very, very fleetingly, so I may have missed this point. In setting up for a general ring spectrum, are you actually needing what's usually called the Adams condition in setting up? I mean, I'm always a little bit confused about where that really becomes relevant. It's usually for identifying the E2 term. On the other hand, it may be you need it to set the spectral sequence up in a decent way. Do you actually use the Adams condition in that paper?
I mean, we use the Adams spectral sequence, the Adams, we try to build some, our technique was we try to build some tower of fibration.
Yeah.
And we prove using the, co-simplicial resolution, we try to build a tower of fibration. Right. And we prove that this tower of fibration also satisfy the Adams conditions, like, but we didn't say anything about the convergence, like the Adams condition. But
right.
Yeah, you're right. We didn't say anything about the convergence.
So okay? when I say the Adams condition, what I'm referring to is this condition that the
we didn't use that. Sorry.
For the spectrum E. Yeah. E lower star of E is a colimit of E star of finite CW things which are E star projective.
Yeah.
Now this condition is not obviously related to setting up the spectral sequence, but it is usually important for.
Yes, you're right. You're right. But to compute these things, you need this extra assumptions. But to setting up,
you don't need it.
You don't need it.
Yeah.
And we didn't use these things in our
yeah.
Thank you.
I mean, another issue that sort of Adams discusses in his, there's a very old paper by Adams in Lecture Notes in Math 99, and he discusses various versions of the Adams spectral sequence, based on cohomology or homology, and that's the place where he basically comes down in favor of the homology version. But even the cohomology version, there are some sort of tricky issues about resolutions,
right?
General,
right?
And I'm not sure they come up in connection with setting up a spectral sequence. It's usually more to do with identifying the E2 term, I think.
Yes, yeah, that's right. But Yeah, we know, but you know, our objective is to understand to identify like E3 time, like E3 or E4 is known because of some work of Bose.
Yeah.
And but we try to understand these things in much more general way to identify using some derived functor in some derived category. Yeah, like the X, to, you know, the X is inside the derived category. So we try to understand these things in more general setting to give a exact formula. But
So
it's not we haven't done anything yet, but we're on this project.
So I mean, I know Barros's work sort of vaguely as well, and so let me ask a very concrete question. If you take the classical atom spectral sequence for I'm talking stably here.
Yes.
Does that machinery compute the Hopf invariant 1 differentials? I mean, is that sort of obvious from the formulism that you're looking at?
So can you repeat it again, the last line? I can't hear the last
Well,
line.
I'm just wondering, I mean, my understanding is Barrows basically knows how to write down the E3 term of the spectral sequence. So that presumably means amongst the other things that come out are very explicit statements about the Hopf invariant 1 differentials.
Okay.
Otherwise, you won't get it without knowing E2, you know, the differentials for E2. So can you say anything about how that shows up? I mean, is it very explicit in terms of what you're saying?
I didn't think it, but definitely I don't have an answer right now. But yeah, I'll definitely, yeah.
Okay.
Sorry, I don't think it. Yeah, I don't have an answer right now.
Yeah.
Sorry, I'll think on it. Yeah.
Yeah, no, sorry. I was just sort of wondering whether you could say anything interesting about that.
No. And thank you for the question. Yeah.
Thanks.
Thank you.
Any other questions?
I have a question, maybe a naive one, but why you call the mapping algebra? So you have some sort of product structure naturally you can define, or?
I don't know because yeah, it comes with an, you know, it comes with an action of some mapping spaces, like, you know, this things. So it's like this is a gadget where you have an additional action of, you can think of this as a field K, the whole thing, and it gives you an action, and they have also respect the mapping, you know, you have, it's not directly, they satisfy, like if you take a product of A, like it's, I don't know the analogy between the actual algebra or these things, but yeah, I'm sorry.
I mean, surely it is. I mean, if you think of it as a graded gadget, it's just the homotopy of it is basically the cohomology of Y with coefficients in A.
Yes, that's true, but it's, then you have to take the home. It's not directly, you know, it's, do you think this is directly an algebra, or if you take the homotopy, then it's definitely a algebra of, you know, cohomology algebra. It's, but not directly, I guess.
Okay, I see what you're saying. Yeah.
And higher homotopy groups have similar algebra structure, like pi 0 is algebra.
Yes.
Because it's cohomology, but in the higher homotopy groups, you have similar observation. Or I just wondered, like, why you call it algebra.
No, that's what I'm saying. If you take the pi 0, then, and sorry, just a second. Just a second. Yeah. And if you take the higher homotopy groups, then, you know, you can think of as a pi 0 of suspension K, right? Suspension K of Y. Like if you try to compute pi K, of this guy, it's like pi 0 of k suspension of y of this object, right? So this is nothing but like the cohomology of suspension y. So it's some shifted cohomology of y. So you have the similar algebra structure, the cohomology algebra structure, if you take the higher homotopy also.
Shifted things doesn't work very well with algebras, but anyway, I'll think about. Thank you. Thanks.
Okay.
I have a question.
Yes.
Okay, let me see. Okay, I'm not muted. You already said something about the E3 page that's been already described by Bowers, right? So
Yes.
I was wondering in that case, so what is the P1 of the mapping space between the island magnetic spaces? Is it easy to describe?
What is the P1 of?
The mapping space here, right, between the island magnetic spaces.
Okay. So you mean
that one? Yeah,
this one, and you want to compute the P1?
Yeah, that's what you need to know, right, for the E3 page.
Yes. No, not really. Not really this one. You need this guy.
Yeah, but for the action, isn't that so?
Yes.
Like in the previous case for the E2, you had the Stirnrod algebra action. So I was trying to understand what is the analog of the Stirnrod algebra if you take the one dimension higher. So that would be P1 of the mapping space of the between the
so like if you want to understand that, like in P1 of any mapping space like X and Y, then these are nothing but the tracks, like all the homotopy class of homotopies.
So it's a groupoid, is that so?
Yes. This is a groupoid.
So you have a groupoid action on the on the thing above.
Right.
So it's like a graded groupoid or something.
Right. Yes.
So is that like a homological algebra over these things, similar to the X group? So is it how the E3 page is described? So I don't know Bauer's work on this. I'm just asking.
Actually, I didn't read the actual computation, but I read the other one where they try to describe the general pages in some derived functor, and yeah, they use some kind of higher tracks, like for the higher, like in particular for E3 page, they use the tracks, like the group, the category enriched over the groupoids. And they use these things, and I don't know, they use any homology. I don't know. Sorry. Yeah, they use the, but definitely they use the categories where they're enriched over groupoids. They use these things, but I don't remember the exact computation. Yeah.
Okay, thank you. There is a question in the chat. No, okay. I thought there's a question. Any other questions? Okay, if not, let's thank the speaker again. Thank you very much, Surojit.
Thank you. Thank you so much. Thank you so much.
Thanks, Surojit.
Thank you.